Welcome to the Science and Exploration of Phobos and Deimos. This is the second to the last lecture, and we're lucky to have Phil Metzer to talk about in situ resource utilization on Phobos and Deimos. Advance the slide, please.
You have too many mice.
So, as usual, due to the audience size, the online audio is limited to myself and the speaker. Unusually, the moderator and the speaker are in the same room for a change, which is quite unusual for this class. But the online audience is encouraged to ask questions and make comments via the chat box. What I will do as moderator is monitor the chat box and collect the questions and relay them back after the. I was hoping to hide today, but I guess I can't. Relay them back at the end of the during the question and answer session. We're very lucky to have Phil Metzer from the Florida Space Institute, University of Central Florida, with us. Dr. Metzer got his PhD at the University of Central Florida. I was actually on his committee, and I remember that well. And he was a somewhat non-traditional student since he had been working at KSC for, what, 15 years by then? Something like that. And has been doing research during that period, prior to his PhD, a range of issues related to the engineering of interfacing with planetary surfaces and atmosphereless surfaces. For instance, he led the agency's work in rocket blast effects for human class missions and has participated on numerous teams, the Lunar Architecture Team, the Mars Architecture Team, Lunar Exploration Analysis Group, and led projects to develop excavators, regolith, conveyance technologies, dust-tolerant disconnects, landing pads, and basically the whole range of surface system technology that require in situ resource utilization. So I'm looking forward to learning something about ISRU, and I give you Dr. Metzer.
Okay, thank you. And we didn't do an audio check before. Okay, good. So I want to mention my co-author, Rob Mueller. Rob was supposed to help present this with me today, but unfortunately he had a medical emergency in his family, and he's overseas now. But a lot of these charts are from Rob, and I'm going to do my best presenting his part of the talk. And this is not working now.
The first click, use the arrow, then after that you can use, the first click on the screen, and then after that you can use the arrow keys on the keyboard.
I think you have to click actually on
Click
the arrow.
on the screen with your cursor.
Like that arrow right there?
There you go.
Okay, so let me mention the Kennedy Space Center Swamp Works. I hope to get a little bit of street cred here for Rob and myself. We co-founded this lab at the Kennedy Space Center, which eventually grew into the Swamp Works. This is a view inside the Swamp Works, where we develop technologies for the Moon, Mars, and asteroids. I've since retired from NASA. Rob is still there as the chief technologist of that group. It includes 4 laboratories: the Applied Chemistry Lab, the Regolith Lab, Electrostatics and Surface Physics Lab, which does dust mitigation, among other things, and finally the Advanced Life Support Lab, which does biology. We have a giant bin for regolith projects, 120 tons of regolith, the largest indoor space regolith testing facility. We've done tests like boulder extraction for the asteroid return mission. We've developed mining robots for this, actually just the bulldozer blade in this picture. This is the Chariot, developed by the Johnson Space Center for mining on the Moon and Mars. There's a small rover, a small mining robot we built called Razor, which digs in both directions at the same time to solve the low gravity problem. We've done testing with it with zero weight on its wheels using offloaders to show that it could mine successfully on a very low gravity body like an asteroid. Testing in the field, showing that we can extract resources from regolith that's been excavated. Flying vehicles. On the left, we see a prospecting vehicle that we've been working on to prospect the ice on the moon. And on the right is that's me looking into a flame trench we built for Morpheus test flights at a simulated lunar field. And we've been working on methods of building concrete. Here we are doing tests with a rocket using simulated landing pad materials. This was kind of a cool project, a 3D printed robot hand. This was an intern that developed and 3D printed this all in one printer pass, a fully functional robot hand in one print operation. And finally, our statuary. We've built we had an artist build for us a statue out of simulated lunar regolith, showing the sort of technologies that we work on. Okay, the objectives today: understand the basic goals and strategies of in situ resource utilization, appreciate the state-of-the-art thinking for ISRU on Phobos and Deimos, and a hint here is there hasn't been enough thinking on this yet. So we're going to be talking a lot about the moon as an analog for Phobos. It doesn't make a lot of sense to say that, but most of our technology work has been for the moon. And so we're going to talk about how to adapt these technologies for a lower gravity environment. We want to try to appreciate the state-of-the-art for resource extraction and how it may apply to Phobos and Deimos. We want to appreciate materials processing, manufacturing, and construction technologies, and see how Phobos and Deimos ISRU may enable Mars surface missions. So first, basic objectives. The following 6 charts I stole from Jerry Sanders and Mike Duke from a NASA presentation. What are space resources? Well, you've got material resources, water, atmospheric constituents on a body like Mars. There's the minerals in the regolith. There's also energy. We've got sunlight. There's darkness to use as a cold sink for heat transfer to make energy. There's environmental resources. Vacuum is a resource. Microgravity could be a resource. There's certain industrial processes that benefit from those environments. And then the location. I put in a lot of information here so that if you want, you can go back through the charts later and look at these. I'm not going to read every word on all of these charts. But ISRU, starting in the upper right-hand corner, begins with, I need to have that little arrow to grab.
Oh, if you just.
There we go. Okay.
No.
Okay, so starting up in this corner, in situ resource extraction and transport, so mining, then moving down to this area, the middle is resource processing. We want to extract things out of what we have mined, and then you can move in 3 directions from that. You can use those processed resources for manufacturing, like 3D printing, or you can, if you're extracting volatiles, then we need to have technologies to store and distribute those volatiles for rocket propellant or breathing air. And then the third direction we could go is construction, building larger structures on the body where we want to work. This is a typical NASA work breakdown structure showing what goes into in situ resource processing utilization. There's resource extraction, materials handling, there's the processing of the resources, there's manufacturing technologies, construction technologies, the consumables, storage and distribution technologies, and then there's the overall systems engineering, modeling, and validating your systems. And so we've done a lot of work in fleshing out each of these categories, figuring out all the technologies that need to be developed. In order for ISRU to make sense, we have to show that there's added value to the space mission. So we're adding complexity to the space mission, but we have to get something back, such as the mass that was saved on the mission, the reliability that we get because we're able to make spare parts during the mission, or other metrics. And so we do this sort of comparison to decide, is it worth doing ISRU or not? And we haven't really done this in any great detail for Phobos and Deimos yet. We've done this in a lot of detail for the Moon and for Mars. We go through a lot of effort in mapping out the schedule. When do all of these technologies have to be developed in order to support different missions? And as far as I know, at the time that I left NASA just a year ago, we hadn't yet done any of this road mapping for a Phobos or Deimos mission to support the surface of Mars. Most of this work has been done for the Moon so far. I just put these up here to give an appreciation for the level of work that we do in mapping this out. Okay, so expected materials that are available on Phobos and Deimos. This is going to be the shortest section of my talk. We don't know. Well, okay, we can do a little better than that. We can make some educated guesses about what's available on Phobos or Deimos. So there's some thinking that they may be similar to D-type or C-type asteroids, and I guess you've been talking about this through the entire semester, so you can tell NASA now what to expect on Phobos or Deimos. But we expect there will be silicate minerals, and those can be chemically processed to extract the elements, including silicon to make solar cells, aluminum or iron or so forth to make metals that we can do manufacturing with. We're hoping that Phobos has some hydrated minerals as a source of water. I understand that's been brought into question. This is a really important question that needs to be answered, because what we're going to do on Phobos to support Mars missions is going to center on water, if water is available. If it is similar to a C-type asteroid, there could possibly be carbon present, and that could be used for making plastics for 3D printing. And of course, there's sunlight there, which is another resource. Because we have a lot more information on the Moon, I'm going to talk about what we do with lunar resources in order to give you an idea of the kinds of technologies we want to develop for Phobos. On the Moon, we know the elemental composition very well because of the samples that were brought back during the Apollo and the Lunicod missions. And so we know that the Moon is about 42% oxygen in its bulk composition. People say there are no ore bodies on the Moon for mining. We don't know of any ore bodies. Well, NASA would disagree with that. As far as we're concerned, the Moon is one big giant ore body for oxygen. The biggest cost of spaceflight is launching oxygen off the Earth. When you use hydrogen and oxygen for rocket propellant, 80% of the weight is the oxygen. So if you can just get the oxygen in space, studies show we can cut the cost of a Mars mission by about a factor of 3 to 5. And I'm going to talk more about that a little bit later. Silicon, metals, calcium, these are all elements that are available in the lunar regolith. In addition to that, we now know that there's ice in the lunar poles, and that provides the missing elements, hydrogen, carbon, and nitrogen. There are also more rare elements, like the regolith elements, phosphorus and potassium in the creep terrain, for example. And there are solar wind implanted elements in the lunar regolith. Okay, with that in mind, well, and I mentioned that there are regional variations, so we know where to go to get the different elements on the Moon. The lunar regolith is thoroughly mixed. All the impacts have broken up the bedrock and thoroughly mixed it so that when you scoop up the regolith, you've got all kinds of different minerals, all kinds of melted glass. And we've wondered if we can sort this out, if we can somehow beneficiate the lunar soil. We don't know if that's possible yet. We've been working on these technologies. Okay, so that's what we're facing on the Moon. Now, on Phobos and Deimos, we want to extract resources out of the regolith or out of the bulk composition of those moons. How are we going to do that? Our thinking is it's not just humans and it's not just robots. It's going to be humans and robots. And so we've been developing these technologies for humans and robots to cooperate. In space, too much crew time is spent performing the repetitive, dull, or dangerous work, and that's why we want the robots. The crew should focus on doing what humans do best, which is solving complex problems with limited information. So we don't need to debate the merits of humans or robots. In the human exploration systems in NASA, we want it to be cooperative. Human robotic systems is a part of NASA that's developing these technologies. The goal is to save crew time, reduce risk to the crew, improve the productivity of the crew, and improve mobility for the crew. I'm just going to let you read this later if you'd like to. Like I said, I put too much information in here so that you can go back and look at it. So for mining, doing it with humans and robots, the first task in mining is prospecting. And so that includes surveying and then assessing, where you would do the more detailed mapping and analysis of the resources. We haven't really done this on anybody in space to any significant degree. We've done remote sensing on the moon, and we've sampled a few sites with the surface missions on the moon. And on Mars, we've got some rovers driving around doing some sampling on the surface. But the degree of mapping and assessment that's necessary for a mining operation is much more beyond this. The next stage after the prospecting is the actual mining. So we have the robots doing the dull, dirty, and dangerous work of digging and loading and hauling and dumping. Then we have machinery that would extract the resources, and these can then be used for manufacturing, or we can use them for construction. Some examples of prospecting that's happened so far or currently in the works. NASA has a Lunar Resource Prospector mission planned to launch, I think it's now around 2019, and that's going to prospect the ice at the south pole of the moon. Rosetta, the Philae lander, was doing some surface analysis. I understand the data is still trickling back. The surface mission is not over yet, but it's a very low data rate. Also, Hayabusa is currently on its way to another asteroid, which will give us some surface data, and the Mars rover missions are getting data. So far, no surface or analysis of Phobos or Deimos, no lander missions there. A little more detail, the prospecting and mining process flow. You locate your mining site. You have to develop technology to anchor to the surface, since we'll be working in very, very low gravity. Develop the methods to excavate and then transfer the mined materials. If we're able to get anything with volatiles, then they would follow one material processing path for extracting the volatiles, collecting and separating the volatiles. If we want to extract oxygen, the thing about extracting oxygen is that then you have to bring the hydrogen from Earth. If you can get ice, then it's already in stoichiometric ratios so that you can have the hydrogen and the oxygen to burn as rocket fuel to recombine. But if we're not worried about the correct stoichiometry for the rocket propellants, we can just get the oxygen alone and bring the hydrogen from Earth, or bring methane from low Earth orbit from Earth. Okay. Next, asteroid mining. There hasn't been a lot of work actually done, but there's been a lot of studies discussing how we might do it. Some of the challenges with mining near-Earth asteroids would be relevant to mining Phobos or Deimos. So for near-Earth asteroids, what we believe are the challenges: they're hard to detect with telescopes, the orbital mechanics of mining, they're moving targets. We would need deep space propulsion to get there. We're not sure about the business case, defining what the ore is that we're going after prior to visiting. There's questions about space mining and international law. That would not be an issue for using Phobos or Deimos to support a government-funded Mars mission. The international law, the Outer Space Treaty, talks about utilizing the resources of space. It does discuss that we will be exploring and using space. The word using is throughout that treaty. So that would not be an issue if it's supporting an exploration mission. The low gravity and the varying gravity field are going to be challenges. Anchoring is likely to be needed. There's a lot of work to be done on developing the anchoring technologies. There may be issues with throwing up dust, which will then come back and interact with the asteroid again later. There's tumbling dynamics, the communications latency for long distances through space, needing to develop robotic autonomy, and then whatever in situ processing we do on the ore needs to be developed. It needs to be able to work in low gravity. And some of these bodies are rubble piles, and the internal structure is not well known. So some of that can be adapted to planning how we're going to mine on Phobos or Deimos. We've done a lot more work developing plans for mining on the moon, and to give you an idea of the sorts of things that we want to do, these are not all going to be relevant to a low gravity body like Phobos or Deimos, but to give you an idea of the types of things, we've laid out what an outpost would look like. There are mining areas, there are landing areas where we've built berms to protect the outpost from the rocket blast during landing. We want to build roads because when you traverse back and forth, you're churning up the regolith and you're making it more and more difficult to drive on. And so on the moon, we wanted to print roads. A lot of this doesn't apply to Phobos. You would probably hop and fly around instead of driving. But some of these things may be relevant. If you're going to have nuclear power, you need to have a place to locate that with appropriate radiation protection and so forth. Okay, some of the tasks that we want to do for surface construction. These, again, were thinking about the moon. Launch and landing pads, beacons and navigations to aid the robots as they're coming and going, lighting systems, communication systems, blast protection berms, roads I already mentioned, refueling infrastructure. If you're producing propellants, then you have to have the infrastructure to collect and distribute and transfer those into your spacecraft. Power systems, how do you recharge your robots? Where do you store the energy to do that? And then providing power to the crew that's there on the surface. Radiation and thermal and micrometeorite shielding, that's going to be an issue on Mars and Phobos just as it is on the moon. Running of cables, utility trenches perhaps, foundations and leveling. We need to completely think about how we're going to attach a habitat to Phobos. And I don't want to read all the rest of this. You can read this later if you'd like. Okay, so on the moon, we knew that we needed to build landing pads. There was a lot of discussion about that early in the Constellation program, but eventually everybody concluded it's true, we're going to have to build landing pads. On Phobos, we don't really know very well yet how the plume of a rocket is going to interact with such a low gravity body. One of the students in the room here is doing that research for the NASA Langley Research Center. It's a lower gravity body, so you don't need as much thrust in order to dock the vehicle with the body. But on the other hand, there's not as much gravity to hold the regolith down, and so you can still disturb it. And you probably won't be doing high velocity sandblasting of your outpost, but you could be throwing dust all over your solar cells and such. We've done a lot of work in NASA on 3D printing with regolith, and there are a number of concepts of how to do this. One concept is to use sulfur, which we know we can get from the lunar regolith. Another concept is to do direct melting of the regolith itself. We've actually developed the ability to use microwaves. That's been studied in some detail. We've used convective heating coils to melt the regolith. We've used solar concentrators. That could actually work from Phobos. You'd need bigger concentrators because you're farther from the sun, but you don't have the dusty atmosphere that you would have on the surface of Mars. So solar concentrators might be a valid approach. We've used infrared lasers. All of these different techniques work. It's just a question of which is the best, which is the most reliable, and requires the least mass and energy on the body. So developing the robots is going to require a bit of work. Some of the technology areas that need further development: sensing and perception, the mobility of the robots, manipulation, the ability to grab things, the human systems interaction, the interface, autonomy, so the robots can do more with less human participation, autonomous rendezvous and docking. If a robot goes out and digs up some regolith, it needs to come back and dock with the resource processing equipment so that it can successfully transfer the mined material into the processor. And then it needs to dock so that it can recharge its own batteries and refresh its propellant so that it can go flying around again. And then all the systems integration, systems engineering. The top robotic technical challenges, I don't want to read all of these, but robotics is a booming area of technology development. And so a lot of these areas are currently making great headway just for terrestrial applications. And so we don't need to use space money to develop all of this. We can adopt the technologies as they're being developed on the Earth, and we call it spinning it in. We spin in to NASA these technologies just by adapting it for the space environment. Okay. So for lunar mining, we've done a lot of work developing the mining robots. We have an annual robotic mining competition, and these are some of the college entries. College teams build these robots. There has to be at least one undergraduate on the team because it's primarily an undergraduate competition, but some of these teams do include graduate students. So if you want to get involved in this, it's too late to have your college sign up this year, but next year there will be another competition. And we're also trying to figure out how to make this more aimed towards low body mining. So we may have rules changes in the future. Some other concepts that universities have developed for mining. This has been a tremendously helpful mining competition. I like to say this, and this is really literally true. Every year I learn more during the 1 week of this mining competition than I do the other 51 weeks of the year. And that's because at NASA we would get typically enough budget to build one prototype robot, either for mining or for resource prospecting. But during this competition we get 40 or 50 delivered to us, and we get to play with it for a full week and find out what works and what doesn't work. We've funded companies like Robotic to build lunar mining robots. This is one that they built called Polaris, which is a transverse bucket wheel. And that's testing it at the robotic mining competition. They brought it down and we did the testing there. And we've built in-house robots. I've already mentioned Razor. There's Razor 1.0, and over here we have Razor 2.0, a very low mass robot, just 50 kilograms. On the moon, it would weigh about a sixth of that, a sixth of what it would, 50 kilograms times 10 meters per second squared, divide by 6 to get the lunar weight. But we've developed it so that it doesn't need any weight on the wheels to be able to mine successfully. Okay, after you've done the mining and you've done the loading and hauling and dumping, what's the next step in extracting and using resources? And that would be chemical processing. So we could make plastics, for example, if we have any organic carbon in Phobos or Deimos. We know that the lunar ice has carbon dioxide in abundance, and so we could crack the CO2 and then combine it with the water in a process known as hydromethanation to make methane. And then polymerizing in the Fischer-Tropsch process, we can make plastics and rubbers. We can also extract metals from the silicate minerals. Iron, aluminum, magnesium, they're abundant on the moon. They're probably abundant in whatever minerals are on Phobos or Deimos. The silicate minerals can also be used for ceramics. And then we can do further processing to make derivative materials. All of these processing tasks require sufficient infrastructure and energy on the body, and so you have to ask the question, is it going to pay back? Are we going to make enough things on that body to pay back launching the infrastructure and launching the energy systems required to operate them? Okay, so this is the flow diagram for the long-term processing of lunar resources. There's two mining camps. You've got mining of the ice, and then you've got mining of the regolith. And so when you mine the ice, you want to distill it. I already mentioned the catalytic cracking and the hydromethanation and the Fischer-Tropsch. So we can make plastics, and then we can do 3D printing of the plastics and the rubbers. We also store the volatiles that have been mined to use as rocket fuel and breathing air and other purposes. Mining the regolith. Okay, this is the heart of this flow diagram right here. These two boxes. This is where we elementally break down the regolith into its constituents. There's a lot of different ways to do it. I've mentioned fluorine processing and molten regolith electrolysis. Both of those processes would then need vacuum distillation to separate out the metals from each other. There's a newer technology that the Marshall Space Flight Center has been developing called Ionic Liquids, and that's where you have an ionic salt or a mixture of salts, and you bring it up to its melting point, which is typically just about 120 degrees centigrade. And at that low temperature, you can actually dissolve minerals. And these ionic liquids are excellent solvents. So for example, you can dissolve 70% of the lunar regolith, and then the thing that doesn't tend to dissolve is silicon dioxide. But with 70% of it dissolved, then you add different salts into this melt, and it will precipitate out one element at a time. You can extract the precipitate, and then you redissolve it, and you can extract the elements one by one. And so this is a method to pick out all the elements. But there's a whole lot of different processes that can be put in place for these two boxes. Once you've got the silicon, then you can make solar cells. When you've got the metals, then you can combine them to make good metal ores. And then you can do 3D printing with the metals. You can do casting with the metals. You can also use the oxides that were not fully reduced to elemental form for ceramics to do ceramic manufacturing. And then you do machining on the parts. So that's the overall flow diagram for how you would process the elements on the moon. Now we would need to adapt that for Phobos or Deimos, taking into account what elements and what minerals and what volatiles we discover on those bodies. Now the goal here is to appreciate, not to fully understand all this, so I've got a lot of pictures, but to appreciate some of these processes. Molten regolith electrolysis is where you melt the minerals, and then you run an electric field, so you've got cathodes and anodes, to run a current through the melt, and this current will then steal oxygen from some of the molten minerals, and so you end up with two material streams. You have a mixture of metals and silicon, which we call a mongrel alloy. We don't know the material properties of it yet, but we're hoping it has some ductility so that it can be used as a poor man's metal. And the other material stream can be used for ceramics. Okay, if you follow this up, take this material stream right here and run it into vacuum distillation, then you can separate out all the elements completely. There was a student at MIT who, for his dissertation, Sam Schreiner, he was also an intern in our lab. He's done full physics-based modeling of molten regolith electrolysis, and he's shown that at different temperatures, you can extract more and more of the elements, get more and more oxygen out of the melt. it would take, according to his modeling, it would take about 5 times more energy to make this mongrel alloy than what it would take on Earth to make high-quality aluminum using bauxite. And the reason it takes so much more energy is because we have a mixture of minerals. We aren't picking out the one mineral that we want. And so we can't use the most energetically advantageous mineral. That's the cost of working with low-grade resources in space rather than scouring the Earth for the high-grade resources and just mining those. Nevertheless, even though it takes so much more energy, it's worth it because this means we don't have to launch things off the Earth. And so it's worth it to use these resources in space, not to bring them back for sale on the Earth. Another example is the fluorine processing, where we use fluorine salt to dissolve the regolith and to break it down elementally. Some of these things, calcium and magnesium, still come out mixed together, and the metals come out mixed together, so you need vacuum distillation to further sort them out. Caustic dissolution using sodium hydroxide, for example, is another process that has been proposed. More simply, if we're just after the oxygen, then we can do hydrogen reduction, and that's when you simply flow hot hydrogen through the regolith, and it scours oxygen and makes water, and then you electrolyze the water to recover the hydrogen, and that gives you oxygen. Ilmenite is the mineral that's most energetically favorable on the moon, but we don't have to sort out the ilmenite. We can perform this process on just generic regolith that we've scooped up off the surface. So this sort of process should also work on Phobos or Deimos to make oxygen. We've tested this on Mauna Kea in Hawaii, and we've shown that we can get about 1 or 2% of the mass of the regolith out in the form of oxygen. Another process is using methane instead of hydrogen, and this is where you melt the regolith instead of reacting it as a dry powder, a solid powder. So you melt the regolith, you react it with methane, it creates water, then you have to do the Sabatier reaction to break down the carbon dioxide, the methane. I'm getting confused here. You get carbon monoxide and water, and then you get methane and water, and subsequent recycling using a catalyst bed, you can reform the methane to recycle it, and you get water, which you have to split to recycle the hydrogen, and you end up with oxygen. Okay, we've tested this also on Mauna Kea in 2010, and we were able to extract oxygen. 15% of the mass of the regolith comes out in the form of oxygen in that sort of testing. We were using a solar concentrator to melt the regolith, and then this was the chemical reactor. This was the test. We had Canadian partners doing the mining, dumping it in a conveying system that used pneumatics to move the regolith in and out of the chemical processor. And then the oxygen that we developed was used to fire a rocket thruster. So we called it dust to thrust. We've also done testing in reduced gravity aircraft to show that pneumatic transport, pneumatic conveying of the regolith can work very successfully in low gravity. Okay, so those are the big building blocks of ISRU. I've talked a lot about the moon because that's where most of the technology development has been done. And so now we're going to talk about some concepts of how we can apply this on Phobos and Deimos in broad terms. The best thing would be if we can get hydrogen on Phobos, if there's hydrated minerals or ice in some form. If we could extract water, then we could electrolyze that water to make hydrogen and oxygen, and it would become part of a network of propellant depots. The way this would work is from Earth, we fill up our rocket using propellants that we made on the Earth, and that gets us to low Earth orbit. Nothing else comes from Earth other than the spacecraft themselves and the humans. All the subsequent propellants come from space. So then we have a lunar mining operation. This mining operation will fuel up the lunar landers, which will then launch off the moon, travel back to low Earth orbit, carrying water, and then they will return and land on the moon to get another load. So the moon will fuel up those vehicles, and it'll also deliver water to low Earth orbit. We have a propellant depot in low Earth orbit, which then fuels up the spacecraft, the Earth-Mars transfer vehicle, which take the humans and all the other equipment to Mars. They arrive in Mars orbit, where there's another propellant depot. This propellant depot gets its water from a Phobos mining operation, if that's possible. So then Phobos sends the water to this depot. The Mars landing vehicle then fuels up using those propellants and lands on the surface of Mars. This should have been a two-way arrow right here. So it lands on the surface. Once you're on the surface, mining operations on Mars create more propellants that allow you to launch back up to the depot in Mars orbit, where additional propellants from Phobos refuel the Earth-Mars transfer vehicle, which allows you to come back home. And then you just deorbit and you use the atmosphere of Earth to brake to land on the Earth, so you don't need a lot of propellants to land on the Earth. So that's the way the network of propellant depots would work, and Phobos would play a critical role in this because it provides the propellants to go back to the Earth, and it provides the propellants to land on Mars, where I'm missing the arrowhead to show landing on Mars. So Phobos would play a crucial role in that. By the way, let me mention, if we cannot mine Phobos, then that means we would have to get all these propellants from the moon, and that means we have to transport all those propellants from low Earth orbit or from the moon to Mars orbit, which means we're burning some of these propellants to move the propellants, which means we have to do a heck of a lot more mining on the moon. And it would dramatically reduce the cost if we can do that mining on Phobos. There was a study that looked into the first pieces of this. This was done at the International Space University. The study was called OASIS, and OASIS is an acronym, and I can't remember what it stands for. I think it stands for Operations and Service Infrastructure in Space. That might be correct. But they define the node 0 is your spaceport on the Earth. Node 1 is your spaceport in low Earth orbit. Node 2 is your spaceport on the moon, where you're doing propellant mining on the moon. And then node 3, they actually declared that it was Phobos. They went through some effort to develop the node 1 propellant depot to describe how big it would have to be, how much power it would need to operate, to electrolyze the water to make hydrogen and oxygen. And by the way, there's other ways to do this. Instead of using hydrogen, you might want to use methane, because methane is a lot easier to store in space. It's higher density, and it doesn't require active cooling systems. All you need is a sunshade. And then methane is the natural propellant for Mars, because the carbon in the atmosphere is far more storable. It's easy to make on Mars. And so you can have your entire system using methane and make it all compatible. So they also went through a little bit of effort fleshing out what the moon mining system would be, but they weren't able to get to Phobos and flesh out what that system would look like. There's actually a commercial rationale for doing this. In addition to supporting NASA missions, every year there are more and more spacecraft launched to geosynchronous orbit from the Earth. The number of spacecraft goes up, 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 and the mass of these spacecraft gets higher and higher and higher on average year by year. So there's a really big business launching things to geosynchronous orbit. So if you just launch them to low Earth orbit and then have a space tug that refuels using propellants from the moon, the study shows that most launch vehicles can cut their launch costs by 40%, because they no longer need to launch an upper stage, and they no longer need to launch the fuel for that upper stage. And the analysis showed that simply launching water from the Earth and then electrolyzing it in orbit to use as rocket fuel would cut the launch cost by 40%. Once you start mining the moon for those propellants, after you've got past your infrastructure startup cost, then the ongoing recurring cost of launching to geosynchronous orbit gets even smaller. So at least a part of this network of propellant depots has a commercial rationale in addition to supporting NASA missions. Okay, another thing you could do on Phobos is you could make heat shields to do entry and descent on Mars. You could use the silicates on Phobos or Deimos combined with a binder that you brought from Earth, a high temperature RTV, and I think that stands for, what does RTV stand for? Does anybody know? Radiothermal vulcanization or something like that. I don't know. It's a rubber that is a high temperature rubber, basically. And the analysis that was done by the SwampWorks showed that doing this, building heat shields on Phobos instead of bringing the heat shields from Earth, would save billions of dollars for a series of 10 or more Mars surface missions. And so that would look like this. This was a piece of artwork we commissioned Pat Rawlings to do.
Room temperature vulcanization.
Room temperature vulcanization, that's RTV. Okay, so it's a material that it's a rubber, you mix it, and it cures at room temperature, but then it's very high temperature rubber. So we actually used RTV and we demonstrated this. This is a 3D printer building a heat shield on Phobos. This is your mining robot delivering the regolith, and then it's being printed concentrically onto this heat shield. And then you've got, I guess this is a launch vehicle down here that pushes it off Phobos. You only need a little bit of delta V to get off of Phobos, launching into Mars orbit. And so this is what the heat shield would look like with your Mars lander. Your Mars lander would come from Earth. It would rendezvous with the heat shield in orbit around Mars. It would fuel up using the propellants that you made on Phobos, hopefully, and then it would use those propellants to begin entry. It would ride through the atmosphere, then it would separate and use additional propellants to land. They built coupons of this using simulated lunar regolith, and because we didn't have any Phobos regolith at the time, any Phobos simulant, but it was mixed with RTV, and they took it out to the NASA Ames Research Center where they put it in the ArcJet facility, and they blew hot Martian composition atmosphere at it, simulating Mars entry at the correct velocities and temperatures of Mars entry, and it ablated as expected. The temperatures on the backside never got very hot. It ablated away, it never crumbled, and it showed that you could successfully land on Mars using regolith from Phobos. Another concept would be to use the regolith on Phobos or Deimos as radiation shielding. You probably wouldn't need to land this because there's plenty of regolith on the surface of Mars, but anything you're doing on Phobos, the crew and the equipment is going to need radiation shielding. Dan Britt is doing research in this area. Leos, who's here in the room, is doing research in this, as are others. The problem with trying to use regolith for radiation shielding is that all of the high Z nuclei in the regolith, those nuclei will shatter when cosmic radiation strike them, and this forms secondary radiation. And so therefore the radiation shield needs to be thick enough to stop the secondaries. If it's not thick enough to stop the secondaries, you can actually enhance the radiation and increase the dose that the crew will experience. Some studies say it may take 2 to 5 meters of thickness for adequate dose reduction. Depends on how conservative your medical doctors are. That number keeps getting bigger and bigger. Last I heard they're trying to say 10 meters because they want it to be just as safe as the surface of the Earth. So depending on what the crew is willing to put up with in terms of radiation dose, you need some substantial thickness. If you had water available, hydrogen is the best radiation shield. If we can get volatiles on Phobos, then using those volatiles would be an excellent shield. And there may be a way to sandwich materials to come up with a very, very effective shielding. Okay, so The terrain on Phobos itself may act as a radiation shield. It's been posited that you could use Stickney Crater to do all of your surface operations. You can tell me, I don't know, but I understand Stickney more or less points toward the surface of Mars. It's tidally locked and it always points that direction. So if you're in Stickney Crater, most of the sky is just a big, beautiful view of Mars. And so the only radiation you're getting off of Mars is the secondary radiation that was knocked off the surface by cosmic radiation. So there is some neutron flux coming from the surface, but it's vastly reduced dose compared to the cosmic radiation itself. Furthermore, you've got Phobos behind you, blocking most of the other hemisphere. And then you've got the walls of Stickney Crater blocking most of the view between Mars and Phobos. And so if you just sit right there, then most of the sky is blocked and you have a great reduction in radiation dose. Okay, another thing that you could do on Phobos or Deimos, but almost everybody I hear talks about using Phobos for this, would be teleoperating on the Martian surface. Right now, NASA doesn't have the budget to build all the equipment needed for Mars missions. The big ticket item, one of the big ticket items will be the landers. So how do you go to Mars and do Mars missions if you can't build the landers? Well, one idea is stay on Phobos and teleoperate on the surface of Mars. And I imagine there'll be more about this in the next lecture, the final lecture of this course. But I want to mention that some of those surface operations will include in situ resources. For example, you may want to build landing pads on the surface of Mars. So astronauts on Phobos can operate the robots on the Martian surface. This avoids the long time delays to the Earth. Right now, we can't build a robot that can operate with a 20-minute time delay and do mining operations. Very simple mining operations, yes, like slot dozing, where the bulldozers just push back and forth, constantly pushing a pile back up. Another robot brings a pile. The robot pushes the pile away again. Slot dozing has been automated in terrestrial mining. But when you go to really complicated mining processes, it really still needs humans in the loop. And we can't do that with Martian to Earth time delays. But if you put humans on Phobos, they could operate the robots on the surface of Mars, doing the mining to create the rocket fuel to come back to the Earth, and building landing pads. So I think this would be a great concept. First of all, it allows us to start doing Mars missions right away. They're doing science on the surface of Mars, but they're also building the landing pads to enable surface missions in the future. And while they're doing it, they're learning how to operate the robots on Mars. So we're advancing the state of the art for robotic autonomy. And therefore, the future missions can, every time we need to build another landing pad on Mars, we can get more and more autonomous until finally we don't need the humans operating on Phobos anymore, and the humans just go to Mars and land on the surface. And so to summarize, and then we'll have questions, ISRU on Phobos and Deimos. Phobos and Deimos are positioned to support Mars surface operations. It's very strategic. And it's a good thing for us that Mars has these bodies. Propellant mining may be a key strategy for affordable Mars campaigns if it can be shown that Phobos and Deimos contain hydrated minerals or ice and that we can get to them. Because then we can set up this network of propellant depots, which studies have shown could cut the cost of Mars missions by upwards of a factor of 5. That's huge. Factor of 5 is really, we cannot overstate how important that would be. Phobos could also be a base for astronauts to teleoperate Martian surface robots. While the astronauts are there doing that, the regolith on Phobos can provide radiation shielding, partially the natural terrain and partially building shields to put over your habitats elsewhere on Phobos. And then more advanced ISRU may extract the metals from the regolith. If there is carbon and hydrogen on Phobos, Then we could make plastics and rubber, so we could do 3D printing. We could also make heat shields, which could make the Mars campaigns more affordable. So that's a top-level view of some of the concepts for utilizing the resources on Phobos and Deimos. A lot of the technologies that we've already developed for the moon, and you can see how those might be adaptable to the Martian, to the Phobos and Deimos environments when we learn more about the composition of those materials and when we learn how to work in low gravity a little better than we can today. And so Dan, are we okay on time?
We're great on time. Thank you very much.
Okay.
And you can actually hear the applause for you for a change.
Because we're all in the room here.
Okay.
All right, a lot of us are in the room.
A lot of us are in the room.
Now, there's 40 more people in the room.
So for questions, we have a few. Jim Had writes, if oxygen is so valuable a resource for ISRU, why isn't the moon in the critical path for humans to Mars? Or any path for that matter?
Okay, that question presupposes that we are using logic in defining NASA's objectives. I'm not sure that's a good assumption. So yeah, I think the moon really needs to be a part of what we do in space. And let me say, in defense of the current plans, they never really did take the moon off the table for mining and resource extraction. They only said that we don't want NASA astronauts to land on the moon. It was still always a part of the plan that we would support commercial companies that will go to the moon and do mining and provide resources back to NASA. And so NASA has had a couple of programs helping these commercial companies develop that capability. Not big programs, there wasn't a lot of money. In fact, I think there was pretty close to zero money. The program was providing NASA expertise to help companies rather than providing them direct financial support. But it was never completely taken off the table to use the moon for resources. Now, my personal opinion is that we should have humans on the moon, partly because it's going to be really hard to start up mining operations without humans present. And I think we can do it a lot faster and in the long run, more affordably if we put humans on the moon. So that's my personal opinion.
Okay, Leslie Gertsch comments that a material is classified as an ore not just by composition, but by economic and technology considerations as well. It would be more precise to say there are no reserves on the moon, although there may be resources there. Just a note, and an ore is really an economic consideration. Is the elemental composition of the body the important information? The feasibility and the energy of mining is given by molecular structure, and it may happen to be only a fraction of the bulk abundance of an element that can be mined.
I missed the last part. There was a lot for me to process all at once.
Okay.
Let me reply to the first part about ore bodies. So thank you, Leslie, for bringing that up, and shame on me for not saying it. I think I can safely say I've never been in a space mining meeting where that hasn't been stated. The community has been very vigilant at making sure everybody knows the definition of an ore is economic. So earlier in the talk, when I said there are no ore bodies, I was just talking about the fact that it's going to be hard to access concentrations of valuable minerals on the moon, because we're not going to start out on the moon by going deep, most likely. We're most likely going to start by scraping regolith and processing that. Eventually, I think people will be going deep into the moon and extracting targeted minerals. I think there's some idea that ilmenite may lay underneath the bottoms of impact craters. There may be some gravitational segregation of ilmenite. Ilmenite's valuable for titanium and for oxygen extraction. So there may be the ability to access economically valuable minerals sometime in the future. But I think right now, oxygen is economically valuable. It makes sense for NASA to go after oxygen. And so I think the whole moon is one big giant ore body of oxygen. It is, I think, economically, all the studies have shown it's economically worth getting the oxygen.
Okay. So the second part of that actually came from someone else. Is the elemental composition of the body the important information? I think the issue is that the feasibility of mining is given by the molecular structure, and that would be a function of how much energy you put in. And it may happen that only a fraction of the bulk abundance of an element can be mined simply because you can't rip it out of the crystal structure.
Yeah,
Comments?
so let me just go back to this chart that for it to make sense to NASA, it's not about can we make a profit. It's not about how much energy does it take to extract the resource or how much mass. It's really a combination of metrics that tells NASA, is it worth doing this for a human, to support a human mission or not? And so the amount of complexity it adds to the mission, the risk that the additional hardware might break, the cost of launching the hardware into space, the amount of energy that the hardware is going to need to perform the mining and processing, the cost of launching the energy equipment, does it require a nuclear reactor, the political cost of not launching a nuclear reactor, there's a lot to it. But these kinds of metrics are what NASA uses to evaluate, and this is what we would mean when we say, is it economic to do this mining in space? There's also the commercial aspect where economic would have its more traditional meaning. Can we mine these elements or these minerals and use them in a way that betters humanity? And we measure the question, this abstract question, are we bettering humanity or not? We measure that by using dollars as an exchange medium. So do you make a profit selling these things that you've mined in space? If you make a profit, then presumably we are bettering humanity overall. I don't know if I addressed what Leslie asked or not, but I hope that helps.
That was a different questioner.
Okay.
And actually, he's in the room. Did that cover it? And no? Okay. Do you want to ask a follow-up question?
Well, please do.
Well, you're not going anywhere, so we'll.
Okay.
If oxygen is lacking on Phobos and Deimos, would it still be feasible / valuable to utilize for a Mars mission, at least in the short term? And I don't think that's actually a problem, because the thing is that all silicates are so full of oxygen that it makes no difference if it's like solid granite versus almost all water from a mass of oxygen point of view. It's just easier to get water out of or oxygen out of water than it is out of granite. Because actually there's more, by mass, there's almost, not quite, but almost as much oxygen in granite as in ice.
Yeah, for the reason that you can't burn a rock. Rocks don't burn because they're already completely oxidized.
Yeah.
So there's plenty of oxygen in every rock.
Ashley points out that we have recently had a seminar on space mining for the class seminars, and that can be viewed, and we put the URL on the chat box. What additional information about the structural integrity of Phobos and Deimos would be necessary in order to develop a plan for mining of these moons? What are the concerns of mining a rubble pile whose porosity and internal composition is largely unknown? And Leslie has a comment on that. Rubble piles will be most effectively processed using bulk mining methods in which the entire body is processed. There are analogous methods in use on Earth. Even so, poor knowledge of the internal structure increases the risk of various types of system failures in any mining method. Comments?
Well, seeing as how Leslie is probably the world's leading expert in asteroid mining, I'm going to go with her answer.
Okay, that was a gracious dodge, yeah. So that worked out. You got a question answered there along the line. How do you verify new rover designs have enough weight to dig in low gravity? Is this accomplished by analysis only, or is there a testing technique?
Okay, so when I was saying earlier that the Razor was able to dig without any weight on wheels, that's not a complete solution to the problem of mining on an asteroid. All that means is that once you've started digging, the vehicle was able to maintain anchoring by the digging process itself. As the two buckets counter-rotated, it was constantly pulling itself to the surface. But there's a lot more to mining in zero gravity than that. You've got to initiate the digging process, and you need some reaction force to do that. And so, and then furthermore, I would never bet my mining site operation on Razor's method of digging. I would never say, well, it can self-anchor while it digs, that's all we need, let's just go with that. Because the first time it hits a rock and the bucket loses contact with the soil, suddenly it's going to float off the surface. So when we said it doesn't need any wheel traction to dig, that's just a minor victory in the big war that we need to wage in developing all these technologies. So there's all kinds of different ideas on how you might dig on an asteroid with essentially zero gravity. One of the simpler ideas is you put a great big net around the entire rock, and then you hang on to the net. So you can get your reaction force by pulling on this net, pulling yourself back down to the surface anywhere you go. So if the body is small enough that you can put a net all the way around it, then that's a good concept. Another idea that JPL talked about for the asteroid return mission is bag it. That's like taking the net to the next level. So you simply bag the entire rock. And if you're trying to get volatiles out of it, if you can bag the entire rock, then you simply heat the entire rock. And hopefully the volatiles will evolve from it. Or you can heat locally on the rock and get volatiles to come out, but as long as it's inside of a bag, then all these volatiles are going to be captured. So there's another idea. Another idea would be to use rocket thrusters, so you're constantly pushing yourself against the rock as you're digging. The problem there is you're throwing away volatiles while you're doing all the digging. You wouldn't really want to do that all the time, maybe hopping around, and as an augmenting system, you would use a thruster to push yourself against the asteroid from time to time. Another method would be mechanically anchoring yourself into the surface by using some sort of a regolith anchor. There have been a lot of concepts developed for that. JPL, Brian Wilcox, had a concept he was developing, and a lot of other people have other concepts. So you can use some sort of a percussive method to drive and anchor into the soil, and then spikes can poke out from it, or a balloon can inflate, something to increase the surface area under the surface. What's missing from all of this is we don't have adequate testing. It's really hard to test any of these technologies in 1G. And in the space station, anything you do is going to be a really small scale test. So we really need to go to an asteroid and test these technologies on an asteroid to perfect them. I kind of danced around there. There's no real good answer. The basic answer is we need to develop the technologies. We haven't done that yet.
Well, I think another aspect of this is that a lot of the SRU focus has been lunar. And lunar has the luxury of gravity, of a decent amount of gravity, versus an asteroid which has truly pathetic amounts of gravity. And so that requires a lot of new thinking, and that's still in its early stages. Next question from Leslie. Accurate models of the internal structure of any small body are crucial. What remote geophysical methods, especially tomographic, is NASA developing?
I can't answer that because there's no central repository of information on what everybody in NASA is doing in that field. There are little projects all over NASA developing different sensor techniques. And I have no way of knowing if anybody is working on tomographic techniques. So I can't answer that.
Well, there are various things that have been proposed, especially in discovery missions, but so far nothing has advanced very far.
So Dan, some of the ideas might be acoustic, I guess, right? Seismic.
Seismic, yeah.
Mm-hmm.
But with seismic, you need an active source, and so you have to blow stuff up. It's a lot of fun, though. How much of an effect would the microgravity environment have on the materials processing methods? What becomes easier and what becomes more difficult?
Okay, great question. I showed you a picture of molten regolith electrolysis, a concept picture. That process presupposes gravity because you end up with two material streams and they separate by gravity. One floats on the other. So they're not going to float. They'll just be intermixed if you don't have any gravity or insufficient gravity and insufficient time. And so one concept is to use centrifugal force and put all your processing technologies on a platform that's rotating just off of the asteroid. Again, I have to say that because we're not developing these technologies yet, because we've been mostly working on the moon and a little bit on Mars, NASA hasn't seriously started to work on any of those questions. There are two groups that I know of that have started working on those questions. That would be Deep Space Industries and Planetary Resources Incorporated. And I don't think they're sharing their concepts because it's intellectual property for them, but they are trying to develop the processes for processing the extracted materials on an asteroid. I've seen Deep Space Industries flowcharts, but I'm not allowed to tell you what I've seen.
Oh well. From Stephanie Gibson, I think you've asked this question before. Why is Phobos considered a preferred landing location for this mission as opposed to Deimos?
You know, I haven't thought about that before. I'm just going to make some guesses based on what I know from having been at NASA for 30 years. Number one is it's a little bit bigger, and I think bigger is better in some ways because there may be a little bit more gravity, maybe a little bit easier to operate on it. And it's closer to the surface. I don't know if that's helpful, except for teleoperating. So if you're at Deimos, it's a very long orbital period, and the synodic period with a point on the surface is going to be extremely long. And so you're not going to fly over your landing site, except, I don't know, what is the synodic period for that?
30 hours.
That short? 30 hours?
Well, I think in an earlier lecture we looked at this, and it turns out that the two-way light time is way shorter than any sort of reasonable reaction time, and the view from Deimos for teleoperating is better, and your length of teleoperating is actually superior.
But hang on a second. So what is the orbital period of Deimos? Is that 30 hours?
Wait, that's what I'm sorry. Orbital period.
Yeah, the orbital period's 30. The rotation period is about 24.
Oh, it's a lot.
So it's like about a 6-hour difference. So it's going to take a lot of those 6 hours to add up to a full synodic period. So it's going to be many days before you fly over the same site on the ground again. Phobos is only going to pass over once every week or something like that?
Phobos is 8 and Deimos is 30.
Yeah. So Phobos would pass over the same spot on the ground 3 times a day.
Yeah.
So I don't know if that has any advantages for teleoperating. For
I guess it
seeing
would
the
depend
surface.
on what you're going to do in teleoperating. But I think each one of them have their own peculiar advantages. One of the problems that Phobos would have is that although it's closer, it's going to have higher tidal effects. So your effective surface attraction to the body is kind of strange, given the Mars tidal effects.
So my understanding is that on the side facing Mars, if you could build a tower 100 meters high, a couple hundred meters high, you could then jump off Phobos.
Well, actually, there are several places where you can walk off Phobos without the tower.
Okay, so the tower has a name. The concept was from Tsiolkovsky, and he proposed building a giant tower on the Earth, build a mountain so high that to launch into space, all you have to do is jump. Yeah. So you could actually do that on Phobos. You could practically build it would be practical to build a tower on Phobos.
It would be trivial in some places.
Yeah, where you could just push off. So if you're going to build heat shields on Phobos, then the amount of propellant you need to get it off of Phobos would be a lot less.
If you can get approximately 15% of the mass out as oxygen, how much regolith would need to be processed to extract enough oxygen for use as rocket propellant?
Okay, I thought I knew the answer until you got to the last 2 words there. If you said to support a human outpost.
Why don't we just say to support a human outpost?
Okay, well, the answer to support a human outpost is you need 1 ton of regolith per year. Because it would be about the same as on the moon, and that was the answer for the moon. So that's trivial. That's less than a cubic yard of regolith. That answer was the result of a lot of study, seriously trying to calculate how much mining needs to be done. So it's totally feasible to support an outpost with all of its oxygen needs by scraping up the top layer of regolith. And then the rovers that do that spend most of their time doing other activities. They only need to spend a small amount of their time actually mining. Now, if you want to make rocket propellant to support all these different activities, like landing on Mars, returning to the Earth, I think Brad Blair, who was at the Colorado School of Mines, he may have done that calculation, but I don't remember the numbers. I'm sorry, I can't say.
When you said that 1 ton of regolith, is that assuming that you're doing like a 70% of the oxygen, or the 1% that you said in?
Yeah, I think
when you do follow-up questions, you need to use one of the microphones. But go ahead.
Well, I'll restate the question. That 1 ton of regolith, was that assume what percent of the oxygen or the mass of the regolith are we assuming we're going to get out? And I don't remember the answer to that one either, but I think it was probably 15%. We were probably assuming the carbothermal, because there were other technologies that would get 42% of the mass out, all the oxygen. But NASA had not done a lot of work developing those concepts. The 2 concepts that had the most development were hydrogen reduction, which gets 1 or 2%, and then carbothermal, which uses methane as the reactant, and that gets about 15%. And I believe we probably used the 15% figure there. And by the way, I'll mention that if you go pull a paper by Bob King and Robert Mueller on mining requirements to support a lunar outpost. If you Google with those kinds of words, you should find it. They went through all of the different activities that a mining robot would need to do to support a lunar outpost, including producing oxygen, building roads, building landing pads, and everything. And they quantified all those different categories.
Okay, what would you do with the leftover materials from ISRU?
Okay. On the moon, they were talking about just dumping it back on the ground. So it's regolith. You've processed it to extract oxygen. The result is it slightly changes the color of the regolith, but there's no other perceivable change. It's still, the particle sizes are all the same. It just looks slightly redder after they reduced it. And then we would just dump this slightly redder regolith back on the ground again. I would like to propose you could also use it for radiation shielding. As long as you've already extracted it and it's available at your outpost, go ahead and put it in bags, sandbags, and use it as shielding. Another thing is, as long as you're doing all this mining, then you should be taking a sample of everything you mine and study it for science. I think that's, in sedimentary geology, a lot of the data came from mining here on the Earth, oil mining. So mining can help provide a lot of samples for scientific analysis. I'm trying to put a really positive spin on mining in space because I'm a pro-mining person.
Good. If ARM is successful in bringing a multi-ton boulder to cislunar orbit, would you use it to demonstrate one or more of your techniques?
That's a really good question. It is not in NASA's plan to do that. The current plan is to put it into high lunar retrograde orbit, where it will be stable for at least 200 years, possibly much longer, and then leave it there. And by the way, this is just a curiosity. I find this more interesting than I really should. But as far as I know, there is no name for the moon of a moon. What do a body that orbits a star is a planet, if it's big enough and clears its orbit. A body that orbits a planet is a moon, but what's a body that orbits a moon? So we need to have a naming contest.
Vice moon.
A vice moon? Yeah, I've heard mini moon. Somebody said they should be called a Botke body.
We could have a contest for that.
Yeah, we should have a contest for that. But so what do you do once it's around the moon? Well, one thing you could do is you could make it crash on the moon and have a real-time impact experiment. Make a great big crater on the moon and study it. Another thing you could do is mine it. And I think that's what we really should do. I would hope that when the time came, that's what we would do. I would hope NASA would have an RFP and then send some money to mining companies, Deep Space Industries, Planetary Resources, or whoever, to develop the technologies and demonstrate those activities. It would present the opportunity for that.
Okay, are there any more questions around the table? You have this rare opportunity to actually ask a verbal rather than a written question. No? Well, we're about done. We're about out of time anyway, so let's thank our speaker once again.